Hello. Good afternoon, everybody. Are you here?
Yes. Hello.
Who's here? Let me see. Participants right here. Let me see. Hey, so cool. Oh, I have 17 students in total. Great. I can tell you, there's one additional student from here. Can you hear me? Everybody, can you hear me?
Yes, we can hear you.
Thank you. Are you able to see me?
Yeah.
Okay. Let's get started. How's life so far? Not bad, right? Are you able to take a walk? Exercise a little bit? Besides, besides chemistry and just eat and sleep? Are you able to do something? I hear people actually borrow dogs from neighbors in order to take a walk. And I find that very interesting. And so I do walk my dog, my puppy, once a day. And let me find her, hold on. My puppy's here. Okay, so the boys in my family, they're all watching TV now. I'm at the corner of my home office. Are you able to see my dog? Hello?
Yeah.
Hello?
So cute.
Yeah. She'll be here with us, okay? And so to get started, let me open up the file, okay? We're gonna do esterification today, and you're supposed to turn in your NMR second visit. Am I right? Are you able to see my screen?
Yes.
Great. So I should say stop video. Am I right? I should just let you focus on the desktop. And let me open this file. Okay, today we will do the reaction. We'll run the reaction with a little bit modified procedure because their photos were collected roughly 7 years ago when we adopted another book, but the procedure very, very, very similar. Okay, it's actually a much better procedure than ours. And I happened to take some photos at that time, and I realized it worked. Okay, it just it's interesting, and this is a experiment that students rank as #1 for the entire 223 training. They rank this esterification #1, their favorite. The reason is the end product is fragrance. Okay. And depending on your molecule assignment, hello, may I have your attention? Or do you know your molecule assignment? Hello? I don't hear anything. Can someone respond? On your lab manual, I'm sorry, on my course packet. Okay, chat, let me see, who's writing? Hello, hello, yes, hello. So can you respond? Yeah, my puppy is a we call multi Shih Tzu mixed, and she's about 6-year-old, and my goodness, she's very attached to me. Best lecture ever. So I like it. With my puppy here, yeah, life is different. I'm more relaxed actually with her around. And so today we will go over this procedure. Okay, first we will have to talk about the reaction. Okay, let me do this. Let me open up the procedure from my desktop. Okay. Oh, okay. So I have 17 participants. Yeah, actually one student already dropped because she changed her major. Okay. All right, students, I want you to take a look at this page. And actually, I uploaded this page, this procedure on Beachboard posting already. And please take a look. Today, you will be doing this reaction depending on your molecule assignments. Okay, some people will be doing the esterification from 1-pentanol. Okay, some will use this isopentyl alcohol. Hey, it says my internet is unstable. I don't know what happened, okay? I'm sitting right next to my modem, okay? And if it's not good enough, you know, it has a lot to do with the traffic, okay, of this neighborhood. Maybe everybody's using the internet at the same time. So there's nothing I can do about that, okay? So depending on your starting material, isopentyl alcohol will give you isopentyl acetate. And this will smell like banana oil, okay? Oh my goodness. And if you have 1-hexanol as a starting point, then you get the hexyl acetate, and I can tell you it smells like apple sauce. So wonderful. It's so pleasant to sniff your end product. Okay, for this reason, this is ranked as #1. And the people who are assigned to do the pentanol, you may complain, machine, you didn't say anything about my pentanol or pentyl acetate. It's so interesting. The smell will be in between banana oil and the applesauce. It's like a combination of both. I don't know why, okay? It so happened that way, okay? So let me tell you, this is an industry that actually produce a lot of fragrance artificially. Okay, so imagine you go to CVS or Walmart, you buy shampoo with the strawberry scent, okay, with lavender scent. Don't even think, okay, the fragrance actually come from the real fruit. No way, no way, okay? You don't go to supermarket and get the juice extracted from the fruit. No, or flowers, they don't. They synthesize in the lab, okay? So this is an industry that actually produce money. Okay, so whatever you do here, okay, means you can sell that product, okay? If you purify it and if you're able to, do the distillation correctly, you collect the product, In fact, every semester students just, put their own product in the car. They bring their own little vial, little glass vial, sample vial home. And then they keep the product. They keep the product in the bathroom sometimes or the shower room. It's just pleasant, okay? This is amazing, okay? I want you to look at the reaction now. Do you see this reaction is showing this arrow, forward reaction and the reverse reaction? Do you see that? Okay. Can someone, someone is chatting and said, yes, very good, thank you, Cindy. Okay, you see this two-way street. For every 4 molecules, roughly, okay, for every 4 molecules recently, you produce from this reaction, one of them will go backwards. this is a reversible reaction. Why do I want to point out this? Ladies and gentlemen, it is because whenever you have a reversible reaction, it means a lot in the production equipment-wise. You have to do something to collect good product in good yield. Understand? So when you have a good yield, that means you can collect more profit or you can lower the cost. Am I right? So let me tell you, in industry, yield means paycheck, okay? And so for this reason, the setup will be different, okay? I want students to respond to me in voice or in writing, okay? If I want to increase the yield, if I want to produce the product at maximum yield, what do I have to do to this reaction process? Can you type answer or can you voice your answer? Bonus point. Hello, am I talking to myself?
Would you like make sure that your limiting reactant is in high like amount when you start?
Thank you. Are you saying one of the reactant can be added in a little bit excess in order to force the reaction to the product side? Is this what you're saying?
Yes.
Thank you. Who is this? Amanda?
It was Aaron.
Oh, Gordon.
Yeah, Aaron Gordon.
I'll write it down. Gordon gets 1 point.
Thank you.
You are so right. Okay, but tell me equipment-wise, what can you do to increase the product? Thank you, Gordon. You can contribute an answer. How to lower the cost, okay? How do you produce more product and make sure this is a complete reaction? I mean, driven to as far as it can be. Gordon gets 1 point. There's one thing you can do. Hello? If
increase the temperature?
Can you increase the temperature depending on whether you have an endothermic reaction or it's an exothermic reaction? Okay, by increasing the temperature, a lot of times it may hurt the yield, but in this case, yes. If you increase the temperature, yes, because it's an endothermic reaction, then you know that means heat is one of your reactant. Then you can force, by increasing the temperature, you're increasing the heat. Okay, so write down heat right here. If this is endothermic, that means it needs heat to move forward. Then you can increase temperature. Now, who said that?
Amanda.
Amanda, very good. Amanda, you get 1 extra point, okay? You're right, a strategy in the factory, yes. One thing we do is increase the reagent amount, either one, okay? Or you can change the temperature, okay? Manipulate heat in order to force the reaction go forward. There's one thing you can do, hello? One more.
Increase pressure?
Huh?
Increase pressure if it's like a gaseous system?
Do you see gas being a product or reactant in this case? If not, you don't increase pressure. Both are liquid, am I right? So increasing pressure on liquid would not mean much. Understand? Okay? There's one more thing you can do. Hello? You can, for reversible reaction, there is one more thing you can do to increase the yield. What is it?
Concentration of reactant?
Concentration of the reactant? Yes, but it's the same thing as adding more reactant by increasing.
Is it the simple distillation setup?
The simple distillation setup is for purification process. You want to purify your product using the simple distillation, but that has nothing to do with the yield or how you want to drive the product. Okay? look at, I mean, the answer is written there, but you didn't catch it. It's written here on this page, okay?
Adding an acid to like catalyze it and make it go like the reaction go faster.
Okay. You're all sharing your thoughts coming from general chemistry training. And let me tell you, unfortunately, having a catalyst, it drives the forward reaction, but it also drives the backward reaction at the same time. Understand?
Yes.
Okay. So, I need to step away. Someone ring the doorbell. Okay. Can we, okay, give me 1 minute. I'll be right back. Okay.
Yeah.
You know, you never know what's emergent out there. Okay, I'm back. Sorry, it was my gardener. And then I realized no one downstairs. Everybody left. They're not supposed to leave the house. Anyway, were you able to figure out what you can do to this reaction in order to increase the production?
Is it adding each reagent like dropwise? Like slowly?
If you add reactants slowly, that usually controls the reaction rate. Okay, you use your product gradually without releasing too much heat. That will be the purpose. Do you get it? But it doesn't really increase the yield. Understand? Okay.
Right.
So I'll give you one more hint. You can do something to the product side also. What do? To force, to help reaction move forward, you can do one thing, one extra thing on the product side. What is it? Let me see who wrote it. Okay. Add a drying solvent. Okay, see who else wrote it. Good job. Okay, you have one product. Evaporated and distilled the product. One product, evaporate and distill the product. Can we isolate the product as welcome back? And okay, I like this word, drying. Can't you add a lot of water under acidic condition? Aha! Guess what? I like this word, drying. Okay? I like this word. Evaporation is not quite. Okay? We're not trying to evaporate the product. Okay? You don't evaporate the product until you purify it. Okay? During the reaction, I will give Pharaoh 1 point. I wouldn't call it a solvent though. I can do something, to remove the water. How about that? Okay, I can remove the product And then I can practice Le Chatelier principle you learned from 111A. Am I right? If I remove this during the reaction, okay, I'll be able to force the reaction to go forward. Do you agree? Yes, okay, so this is the strategy. So it means a lot to the equipment, I said that, to the manufacturing equipment when you run a reversible reaction, okay? When you happen to have a reaction written this way, yeah, chemist tells the production side, hello, this is the reversible. Oh, then they will know, hey, I have to adjust the equipment in a certain way in order to produce the product at maximum amount. Understand? Okay, this is real. This is real, okay? Now, try to understand if I put a, okay, hydrogen plus right at this now, okay? It means acid proton is a catalyst, okay? It is not reactant, it's not product, it's a catalyst. It involved in the reaction, it helps to speed up the reaction, but it gets regenerated, it's not consumed, okay? It gets regenerated in the reaction, okay? At the end, you will still get a lot of acid back, okay? So you may say, machine, is acetic acid being used this time acidic enough to catalyze this? I can tell you no, because it is not a strong acid. So it doesn't really catalyze the reaction. You rely on sulfuric acid in the lab procedure, okay? That release proton generously, quickly, okay? And that will serve as a catalyst with no problem, okay? And so let me tell you, this is a reaction with only two reactants put together. And then the third ingredient will be a couple drops of sulfuric acid. And then you start cooking, okay? It will add heat to it, okay? And so let me do this. Let me do this photo presentation right here, okay? And this is just one example of what the reaction is taking place today. Besides, depending on your molecule assignment, you will be making different molecules. So on the worksheet, I want you to write your own reaction that you're responsible for, okay? Some people will be doing this. It will be the same process. You all do the same procedure, okay? Following this photo, okay? Our setup right here is a little bit different, but I told you this is a better one, okay? So I kept the photo and I want to show you the process, okay? Okay, now I see according to the procedure, and that's the same for you guys and the existing lab manual, okay? You combine your acetic acid in glacial acidic form. Did anyone look up what glacial acidic acid is? Can you respond? And I can give you a point. Okay, so three students got bonus so far. Can you tell me, did you look up this word, glacial acidic acid? This is the same as what we mentioned in the lab manual. Glacial acidic acid. How is this different than the acidic acid you encounter in your life? Hey, someone said. Anhydrous acidic acid. You're right, Farrell. Can't you add a lot of water under acidic condition? Well, by looking at the reaction, the equation writing, remember water is a product. So if you add a lot of water to that reaction, it only forces the reaction going backwards. Am I right? So don't do that, okay? So Farrell, you get the point, okay? This is anhydrous acidic acid, and you get another point. So why do I want anhydrous? It is obvious because I don't want water. Having water there in the reaction mixture will just push the reaction backwards, right? And that's the reason, okay? We use glacial acetic acid. We don't use regular acetic acid in water already. No, okay? We don't want the water at all. We want totally free of water. And why is this glacial word being used in this region? It is because it's free of water. And so if the vinegar, okay, at home is free of water, actually this molecule will solidify at room temperature. It looks like glacial, okay? It looks like ice, and so it is described as glacial acetic acid, okay? Okay, and so we talked about this excessive amount. Okay, I want to go back to this reaction scheme, okay, right here. And I want to share with you my industrial experience, okay? We're coming back again. And Miss Jean actually happened to be working on the esterification for 4 to 5 years at BP, British Petroleum. That was my first employer. I talked about that all the time, okay? And, you know, this is a company that makes ester, polyester. Polyester means a long chain of the same repeating unit, all ester group, okay? So every day, okay, I go to the factory, okay, and the lab, I can produce ester from the alcohol and the acid, okay? So in this example right here, in this lab manual, we're saying we add acetic acid or glacial acetic acid in a little bit higher quantity in moles, am I right? Okay, but let me tell you, in industry, we don't do that. We do excess amount with alcohol. And this is true. This is so true. And I tell you why, okay? If you look up the boiling point of the two, you will realize alcohol is actually lower boiling point compared to the acid, okay? You may say, Ms. Jean, is that true? I have hydrogen bonding here. And acid, yeah, hydrogen bonding here. And this is a big molecule. I can tell you, you're right, it is a bigger molecule, but look at this. This is non-polar. There's no polarity here, but look at this acid right here. It has carbonyl group. So this is another polar group present in the acid. For this reason, acid has a higher boiling point compared to alcohol. Okay? This is higher boiling point compared to that. Okay, so what does it mean, Ms. Jean? Why do you add this alcohol in a little bit excess, meaning larger quantity? Because during the reaction, this is more volatile than, right? When you apply heat, then this will fly away with higher tendency. The alcohol will fly away more when you heat it. Am I right? Yes, this is what happened. Okay, so in order to keep this in 1-to-1 ratio, or in order to keep this quantity always in larger amounts, okay, we can compensate for the loss caused by the heat evaporation. Understand? So this is what we do in industry. Okay, we add alcohol in order to compensate for the loss caused by evaporation because alcohol has lower boiling point. Okay, get it? Yes, the second reason I have to share with you, okay? In the company, in the factory, we actually run this reaction under nitrogen. Aha! What does it mean, Ms. Jean? Nitrogen. Why do I want nitrogen? Because I don't want oxygen. I don't want ambient condition. I don't want oxygen from the air. I want to keep it out, or else there will be oxidation reaction to the alcohol, am I right? Oh, yeah. Alcohol, primary alcohol will oxidize to, help me, can you answer your question? Answer this question. Answer this question. If primary alcohol is oxidized, what does it produce?
Carboxylic acid.
Who said that?
Aaron.
Aaron again. My goodness, you're super. You get 1 point. But actually, between the primary alcohol and the acid, there is something in between. Let me read who's writing. Oh, okay. So, ketone? Amanda, ketone will have to come from secondary alcohol. Secondary alcohol oxidized to ketone. Thank you. Who says aldehyde? Thank you. I think Jocelyn responded faster. Okay. Thank you, Lazo. You get 1 point. Yes. Primary alcohol will become, thank you. Okay. Primary alcohol will turn into aldehyde when it oxidizes, and then aldehyde will turn into carboxylic acid when it is oxidized. For this reason, when we run the reaction in industry, yes, we use nitrogen and purge through nitrogen. Purge the nitrogen through the reaction mixture. For the entire reaction, we want the nitrogen on. And so what does it mean? Hey, when you purge gas through reaction mixture, do you purge some liquid out at the same time? And because you're heating it, some of the alcohol will just fly away, am I right? When you heat and then purge, okay, with a lot of pressure of air, nitrogen, yes. So for this reason, we have to add roughly 10% extra. In terms of moles, it has to be added 10% extra to compensate for the loss due to low boiling point, lower boiling point compared to the other. The other thing is because you purge with nitrogen at all time. Okay? And so tell me, what is the purpose of nitrogen? You want to keep the oxygen out. Am I right? Okay. So I'm sharing this because it is 100% based on painful experience. Okay. The whole industry know how to maximize the yield based on all the suggestions, all the points I brought up right here when I talk about this reaction. Is this real? Okay, Miss Jane run this reaction for 4 to 5 years. I know about the yield, okay? Okay, so let me move forward and let me continue with my photo, okay? Let's see right here, okay? Why is glacial acetic acid used in here? Can we add the alcohol in excess amount instead? Yes, definitely. Okay, so what is the purpose of sulfuric acid? I asked you this question and I want you to help me later, okay, when I talk about sulfuric acid being the catalyst, okay? You combine the reactions together, now you add the sulfuric acid as catalyst and then mix. Then, I want you to watch out. The two acids were all corrosive, okay? Ooh, dangerous, yes, okay? Especially sulfuric acid is so nasty, okay? Then you set it up. This is called reflux assembly. You learned about reflux before, have you? I did ask you to read this part of reading assignment. This is coming from your green little connection book, okay? Okay, so what is a reflux? You just need, a round bottom flask right here. Okay, you saw it, okay? Then you need a condenser. I probably cannot see very well right here, okay? Let me tell you, these photos come from 7 years ago, okay? At that time, we didn't have iPhone, good camera from iPhone yet, okay? So students were just taking the photo using their digital camera, and this is the result. We didn't have a high resolution, okay? But I think you understand, okay? And you clamp, okay? You put your condenser right here, water in, water out, and that's called reflux. And you may say, Miss Jean, I see something weird right here. Okay, no, this is a drying tube, okay? This is a plastic piece of equipment, and we put drying agent right in here. Remember, we're trying to remove moisture in order to force the reaction go forward to the product side. This is the equipment, okay, for the water removal process. Yeah, you bet, okay? In the lab, it's like this. In the factory, okay, we just use the nitrogen to purge and then purge and then purge, and then we just condense the vapor. Okay, use a condenser, a huge condenser, and that will serve the purpose of removing water. Okay, so let me tell you, the reflux apparatus is very simple, and you all the time you see this boiling, okay, this boiling process, okay, but you don't care about the temperature reading at all, okay, as long as it's boiling, as long as the heat is not terminated, and as long as, I have to show you something else, okay? As long as you're able to see the reflux ring, level of the reflux ring kept below the water entrance point. Remember the long condenser right here? The water inlet and water outlet? Okay, so you will see reaction mixture is producing some vapor from beneath, okay? And then condense. Vapor will hit the cold surface of the water condenser and condense back. You will see sweating, okay? Vapor going up and going down, condensed into liquid. Okay, and so you don't watch temperature, but you watch this reflux ring we call. Okay, this is the only thing we watch in the lab. Okay, but in the factory we watch many things. We definitely will put a reaction. We definitely will put a thermometer in the reactor. And if you, for your information, do you know the reactor size machine was dealing with when I was a chemist at BP? You were talking about 6 metric ton. That is the smallest one. The smallest reactor is 6 metric ton. Okay, the biggest one I've ever seen is 20 metric ton. Okay, the same size as what? Maybe like my house. Yeah, it's probably the same size as my house. I mean, just the ground floor part. Yeah. Okay, it's huge. Yeah. Okay. And let me tell you, you will see this evaporation, condensation all the time. And in the lab, this is all you watch out for. Okay, so reflux, you don't care about the temperature reading in the lab. You care to see whether you're losing your liquid from the reaction mixture and you want to capture them, okay? And if there's water, because I capture the water molecules at the top, so you know, not all the water will be condensed back, okay? Some will be captured here, okay? And so you remember how to set up, okay? So I'm not gonna go to the detail, and okay, we start adding the heat. And tell me, how long do you wanna cook it? How long do you wanna cook it for? according to the procedure, you only need 1 or 2 hours, right? Yeah, an hour, thank you. You're right, Aaron, it is 1 hour. So when do you start the 1 hour? Tell me. When do you start the clock? How do you know you want to start your timer of 1 hour? When it is boiling? When it starts boiling? No, not really. Right at the beginning of the vapor forming at the ring. My goodness, Aaron, you are born to do chemistry. You are right. When you see the first sign of, we call reflux ring right here. When you see the first drop condense from the condenser, that is the indication the reaction actually got started. Do you get it? Okay, this is, and all the lab and all scientists on Earth knows this is what we officially call reaction starts, okay? So it's not from observing what's underneath. We care about the reflux ring, okay? All right, thank you, Aaron. You get another point. My goodness, you got 3 points already, okay? And I want the rest of you to participate the discussion, okay? You really have a great potential. The more you think, and a lot of details associated with this reaction, okay? The more you think about the details, the better you are as a chemist, okay? And actually overall as a scientist. And you may say, Ms. Jean, I want to work in the hospital, so why do I have to get trained this way? Hey, who says the healthcare professional don't need to learn to observe? This is a critical point, okay? It is just like your patient start breathing. Of course, it's important, okay? All right, so at the end, yes, let me see. I want to see your comment, okay? Make me your +1 for Jean. Troy, guess what? So many students want to throw a party, and especially after this crisis, we're a different person, okay? We become a different kind of a creature. We all have seen our own limits, okay? With capability limit there. Yes, is that still on? Do you guys want to do it? Okay, we name a date. We meet in the park. How about that? Banana oil for everyone. I'll bring, okay. Okay, all right. At the end of the semester, when we're allowed to go out, let's party. I mean, we all need to go wild, right? All right, I agree with you. I agree with you, okay? I will bring 2 bottles of plum wine. Okay, all right. Top, okay, sure, okay. All right. Can we go back and enjoy our banana oil? Okay, look at it. Look at it. All right, here. All right, all right, all right. What is soju? Oh, you told me this is the plum wine on the melon. Oh, this is the wine over the melon. Did you say that? You're the one making that suggestion, I remember. Korean alcohol. By the way, are we allowed to party in public with wine? I don't know. Oh, so much fun. Yes, yes, yes. Okay, I'll find out if it's legal, okay? I have to make sure we're doing something legal, not getting ourselves in trouble, okay? All right. So, okay, for now, hey, let's go back to our banana oil, okay? The banana oil is, my goodness, in the reaction mixture, it goes like, ooh, it is brown fluid. Is that real? Yes, unfortunately, yes. The way we set it up, we didn't prevent the oxygen from coming in, okay? So oxidation occurred, and You don't get the very beautiful look right here. Yeah, because oxidation of alcohol and some undesirable oxidation makes it so ugly, okay? But regardless, we turn off the heat, okay? And we will start working up. We call it work up. Work up, what is the purpose of work up? It is to remove and remove the impurities. If you add acid, you want to remove or kill all the acids. You just don't want acid in your product, am I right? No way. Who wants acid in the product? Okay, acid will cause side reaction, am I right? Okay, and side reaction means you may hydrolyze the product. Your very precious banana oil will be ruined, okay, if you leave that acid there, okay? And then, okay, you pour the liquid, that ugly brown fluid out. We purify it by acid base. Look at this big word, extraction. For those who are trained in my class, remember this is the tea caffeine experiment. We extract caffeine molecule from the tea by extraction experiment. Yes, we did it, okay? And you use, how do you name this apparatus? It's called separative funnel, right? Okay, and I tell you, I like this method much more compared to the one described in our manual. It says we do it in the as a centrifuge tube. My goodness, I hate it, okay? This is professional. If you want to do extraction, please do it here, okay? Okay, cool it down and pour. And I can get rid of the acid by adding some water first, okay? I can cool it down further, okay? And I can start adding the very, very important reagent right here needs to be introduced to neutralize the acid. What is it? What is mentioned here in the lab manual? And it's the same. It is sodium bicarbonate. You're right, but you're missing the word sodium. Thank you, Farrell. Thank you, Farrell. Thank you, Farrell. I think I should give you 1 point, okay? You should give me sodium, sodium bicarbonate. It is the same baking soda solution, okay? Give her 1/2, okay? All right. Okay, she made it up. I mean, she made up the answer totally, now perfect. Okay, okay, Troy, be nice, okay? We're online, okay? And we want to encourage students who respond, okay? This isolation has been hard. What do you mean? What do you mean? Isolation has been hard? No. You just put your brown ugly fluid here, and then you will introduce sodium bicarbonate, that baking soda solution, slowly, okay? You add it slowly, portion by portion, and that baking soda solution is just like a 7-Up, okay, without sugar, okay? That 7-Up solution without sugar will neutralize the acid for you. And let me tell you, there is one big indication that reaction is actually ongoing. The neutralization is taking place. Tell me, what is the indication? Hey, bonus point, bonus point. Type your answer, hello. What is a good indication that neutralization is taking place? Oh, some other noise. 2 layers separate? No, this is not indication where, you know, neutralization is taking place. It's cloudy? No, not really. Formation, who said that? Farrell, you got another point. Sure, you're awesome. You earned 4 points already. Smell? Nathan, let me ask you this. Nathan, have I ever asked you to clean up the acid spill in the lab? And do you smell it? Do I ask you to use baking soda solution, the sodium bicarbonate, okay, sitting on top of the sink? Okay, I usually ask students to spray over the acid spill, and then you will see foaming, the CO2 foaming, okay? How does she know? Well, Pharaoh, I know you're naturally intelligent, okay? But I can tell you that reaction is written in the lab manual too, okay? Sorry, I thought you meant the formation of, not yet, okay? Okay, yeah. My lab write-up, yes, okay. It's actually in there, yeah. If you wrote in the lab in the lab manual, we already mentioned in the note, okay, in the back, special notes, okay, it's there, that reaction's there, okay. I can tell you, baking soda is probably the most popular, I would say top 5 chemicals, what consumption wise, it's top 5 in volume consumed in United States. Okay? And I want to invite you to tell me, are you able to figure out, okay, besides acid-base reaction, what is the #1 application of baking soda? Don't tell me it's 7-Up, okay? Yeah, we drink, but it's a very small portion. The #1 application of sodium bicarbonate in the United States, maybe worldwide. Do you know what that is? Do you know what that is? The application is fire extinguisher. Indigestion. Cindy, I would like to encourage you by giving you 1 point. Okay. In the old days, okay, Cindy Vu, I want to give you 1 point, okay? The reason is there's something being done in the past. Cleaning, cleaning in our lab, yes, okay. Okay, but in the world, #1 application is fire extinguisher, okay? But I want to get back to Cindy's suggestion. Yes, you know, in the old days, when doctor treats the hyperacidity reflux, actually in your stomach, okay, a lot of patients, okay, who had hyperacidity, that means a lot of your stomach juice actually reflux between the stomach and your mouth, yes. and that means it's an indication you have ulcer, am I right? In the old days, yes, the doctors actually treat the patients with sodium bicarbonate, just neutralize the acid inside the stomach, okay? Yes, in the old days, I'm talking about maybe 50 years ago, but not anymore. Do you know the reason? Because the sodium is bad to the heart, am I right? So doctors don't do that anymore, okay? All right, now let me get back to the application of sodium bicarbonate. Why is it used as a fire extinguisher? Because sodium bicarbonate, if you burn it, if you put on fire, it will produce CO2 and water. Okay, yes. And so do you see in the fire season, you see helicopter from the sky, sometimes they spray the white powder. They sprinkle the white powder from helicopter. What for? Yes, that is baking soda they're spraying, okay? Because it produces CO2 that will repel the oxygen. At the same time, the water extinguish the fire. because water naturally put out fire. Am I right? Yeah, so that is number one application. Okay, so for this reason, when you add sodium bicarbonate into acidic solution, it forms also CO2, and you have to watch out. When you shake it, you want to be a little bit gentle, okay? And you want to add the baking soda solution in small portions, or else the whole solution will foam up and you will lose your very precious product. Understand? This is all common sense, okay? All right. All right, let me go back to the photo. Okay, now you see this 2-layer. Oh, you know, this brown ugly layer is your fragrance layer, okay? And the bottom layer is gonna be your aqueous layer, right? Because you introduced baking soda. Am I right? Baking soda in solution, all right? And because the organic layer is lighter in density, so it's on top, okay? So drain and then wash, okay? And then, my goodness, the aqueous layer does not have this contamination of the color molecules anymore. And, okay, you will see 2-layer at all time because water and the organic layer don't like to dissolve each other. And then you drain the bottom layer, you keep the top layer. That is your very precious product, okay? It's so ugly, right? It's so ugly. And before we distill, we want you to add anhydrous granule of sodium sulfate. Again, what is the purpose? Because I wrote it down here. You know it's for drying purpose, right? All right, let me see who's answering now. Yes, drying agent. Amanda, I like your answer, but can you tell me how much drying agent do you want to add to this solution? Can you suggest for better yield? Oh, Cindy, I have to respond to you. When you add drying agent, if you're not careful, you will kill the yield because the particles will just absorb your very precious product. Okay, so it's not for yield purpose. Okay, 2 to 3 drops? No way, no way. Hello, we're using powder now. Hello, 2 to 3 ml? Hey, wait a minute. We're talking about powder, okay? Hey, ho. You're too fast, okay? Removing water at about a thumb worth length, and then just enough to give snow globe effect. And clump. Oh, I like this description. Clump. It's describing the look. Small amount of sodium. No. You don't add sodium, okay? Well, what do you mean sodium? Sodium metal? No. About 1 gram? No. Wait a minute. You be careful with this amount, okay? I think you use drying agent when you run your spinach experiment. Do you remember? Hey, what's wrong with my internet? I'm sitting right next to my modem, okay? Isn't the tip of the spatula? Yes. But there is an indication in the solution look that you can pay attention to when the solution is dry. Now it's brown fluid, so it's more difficult to see, okay? I like the answer proposed by Aaron again. Aaron, you're collecting your 4th point today, okay? I'm very proud of you. That means you really read a lot of details. I'm proud of you. It's something to do with clumps, okay? If you know, you want to dry your solution, okay? Whenever you run extraction experiment, you have to add drying agent to the layer you want to keep, At the end, you add the drying agent. At the end, after you completely separate, okay, this aqueous layer and you pour your desirable organic layer out, immediately you want to treat it with the drying agent because you want to remove all the moisture from the extraction. Remember, you're shaking the septary funnel. From this mechanical energy you add to the solution when you shake two layers together. The water layer will be contaminated with the organic layer. The organic layer will be contaminated with the water as well. The water droplets are there. So you have to add drying agent, okay? But the best indication will be forming clumps, means that the drying agent is being a glue, functioning as a glue to glue the particles together. So why am I seeing clumps? Because the particles are being attacked by water together and forms snowball. You're right, Aaron, okay? That is the indication. So you add the drying agent small portion by small portion. Okay, so let's say tip size of the spatula you add in, okay, shake. Okay, swirl the solution around and you will see clumps. Okay, when you see clumps, that means, hey, go ahead, add more. Okay, because I know there's a lot of water there, okay? Until you introduce the additional small amount of the drying agent, they don't form clumps anymore. They are free flow powder. Hey, just like sand going up and down. So that means those powder, the drying agent, not glued down by water anymore. That means the solution is now moisture free. Do you agree? Yes. So this is how chemists determine how much amount of the drying agent you need. It is all coming from your own observation. We shouldn't be giving you quantity at all. Do you get it? Do you get it? Hey, my puppy is answering yes. Okay, let me see. Are you able to understand my message? 8 new. Isn't the tip of the spatula? Yes, but you add that spatula tip, then you will swirl. Then you will, you're cutting down. Okay, yes, you got the message, okay? You have to swirl the solution at the same time you observe the powder, okay? If it is clumps, that means, hey, a lot of moisture there. That's why I'm making the snowball, okay? Because the water is the glue. But if I don't see any more clumps and I see free flow powder, that's indication the solution is dry. Okay? All right. After that, go ahead and pour the liquid out carefully without introducing the drying agent, or go ahead and grab the filter. Every time you filter something, you will lose your product, okay? You know that, okay? So we suggest you can just pour carefully. And then we do micro distillation, okay? You distill. Okay, you distill the product. Okay, I want to open up another file, okay? So don't you like to run this experiment without messing around with your glassware? I can tell you, most students were saying, Ms. Jean, I would rather collect the product myself. Yeah, I agree with you, okay? It's more fun when you create your own fragrance in the lab. And didn't I tell you one time my students actually, he works in the bar as a bartender. And he was able to collect a pure product from his own banana oil synthesis, okay? And he brought to his client in the bar, at the bar. I don't know if he forced the client to enjoy by drinking it. I don't know, okay? Yes, I can tell you, this is rank #1 for a reason, okay? And some student even wrote to me, Ms. Jean, can we come to the fall semester? If you teach this lab, we want to come to your lab and observe. Yes, you're welcome to do so, okay? Smell the apple, okay? Smell the banana. And you probably get inspired to become a fragrance chemist, who knows, okay? Yes, I invite students who are, interested in observing this experiment in the fall, please contact me and you can come to my lab to observe, okay? Enjoy the fragrance, okay? All right, and let's do purification now. Micro distillation, okay? Have you noticed? Okay, it looks just like my simple distillation setup, but I don't use condenser anymore, okay? I just put the adapter directly at the tip. We call this three-way distillation head. Yeah, I want to omit the condenser completely. And this is a short version of distillation. Why do I do that? Because in this big surface of the inner tube of the condenser will also take away some of my product, okay? I don't want to lose my precious product. That's why I cut short, okay? And there's another way to do it, and I call this, okay, so you can just distill this way, okay? There's another way to do it, okay? We call micro distillation apparatus. And this is a piece of equipment I will ask all of you to check out. Use your ID, and they will give you this utility clamp, okay? They will give you this one piece apparatus with a side arm already built in, okay? And they will give you septum. And so all you have to do is pour the liquid in, add boiling chips, okay, seal on the top, okay, and you put your thermometer in. And the thermometer tip, okay, it has to be free from touching the glassware. Oh, you know that, okay? And it has to be 1 centimeter below the side arm, okay, in order to record the temperature correctly. Yes, you want to make sure, okay, the thermometer tip is in the right position. You learned that from simple distillation. I want you to review that, okay? And then what do? You can put some, okay, you put your, you connect the heat, okay? And you may want to add the sand into the well of the heating mantle so you can save the heat, okay? Make sure this is energy efficient, okay? And you clean up a vial in order to collect your product like this, okay? One hand hold the thermometer, the other hand you will just, receive the distillate in a very tight range of boiling point. So your target molecule will have a specific range of boiling point. And you want to stay tight. You only want to collect your own product, okay? At the beginning, you will probably see, some forerun, we call, okay, some of the unreacted alcohol still, okay, still remain in your product layer, that brown, ugly fluid, yes, okay? So some of the alcohol is still there, okay, so collect it, okay? But that, that vial is not your target product. And so you go ahead, concentrate on the tight range of the boiling point of your target product, okay? And I gave the full description right here. And guess what? At the end, I want to show you that photo because this is a real photo, okay? At the end, wait a minute, where is that? It is this photo. You see how people give me the smiling face when they enjoy the smell of banana oil or the apple sauce? I can tell you every year I see this, okay? A lot of students, they take pride in what they did, and then they enjoy the product at the end. So much fun. Rank #1, okay? All right, am I done? No, I'm not done. Okay, I have to talk about the mechanism. Now tell me, have you had the exposure to esterification reaction? Where is it? From the lecture professor? Let me see. What's your comment? Yes. Oh, great. No, Cindy. All right. Dr. Schranz talked about it today. Thank you. Cindy. All right. Let me make it up to you, okay? All right. Let's do this. Yeah, one more. All right. Okay. All right. Let's enjoy the mechanism together. Okay. Okay. Bonus point opportunity. What's wrong with this reaction writing now? I don't like it, okay? I want you to criticize. You are using the carboxylic acid, you're using alcohol, and then catalyst, okay, and then ester. I don't like this reaction writing, okay, but you know, I use this slide with a purpose. I want you to examine what's wrong with it. Remember my lecture from the start? Bonus point. Didn't show acid and water. The heat is not missing, okay? It's reversible. Who said that? Brittany, thank you. Brittany gets 1 point. It's not reversible, okay? Whoever wrote this page didn't have common sense, okay? For this reaction, everybody knows it's a reversible reaction, okay? Thank you. Brittany gets 1 point. What else? What else is missing? No heat? We don't, I can tell you, Amanda, I can tell you this reaction will proceed without heat also. It's just slower, okay? And you're right, Aaron. Water is missing in the product side. Amanda, yes. Amanda put it in the perfect writing, and I'll give you 1 more point, okay? Aaron, please give that point to Amanda, okay? Yes, because she wrote a perfect answer, water and product. You're right. Water should be included here. How many molecules water? Just 1, okay? And this should be a reversible reaction. Let me see. Thank you. You're right. You get 1 point, all right? I want you to see the mechanism, okay, everybody? Mechanism. Remember acid? Acidic proton is your catalyst, okay? And Miss Jean, is the mechanism right or not? Not right. It is right one, okay? It is the right one, okay? Although I didn't like the writing of the equation, I like this part. Student asked me, Miss Jean, are you serious? Does acid actually come to the acid? Yes. Okay, this acid doesn't know this, you know, the reactant is an acid. No, it doesn't know, but it's interested in something else, okay? It's interested in something else. This is why I want to create the opportunity for for your answer, okay? This proton is coming to the oxygen. But there's another oxygen. Why? Miss Jean, tell me why. No, I don't want to tell you why. You tell me why. How about that? Why is this hydrogen plus interested in this oxygen, not this oxygen? Look at the difference. Ketone needs to be protonated, yes? OH is a weak nucleophile. No, I'm not asking you. Well, did you say this is a nucleophile? You have another OH right here. This is from alcohol. The alcohol is looking for that alcohol itself is a nucleophile. It's nucleophilic because of a lone pair. Okay? All right, now students, can you do me a favor? On the reaction rating part, do you want to put a partially positive right here on the carbonyl group? Can you do that? Yes. Okay. Okay, let me read your answer. It has a resonance so that carbon will be more electrophilic to have the faster reaction. Let me tell you, this is the consequence, okay? It has resonance. It has a resonance. Patty, I want you to think a little bit, one more step. Protonation of acid, yes, 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 yes. Oxygen is electron pooling. Yeah. Nathan, you're on the right direction. This oxygen is electron pooling, yeah. And here it is showing dipole moment right here, okay? So it is partially positive here on this carbon, and this oxygen is giving you, negative delta, you know that, right? And it can form a bond. But my question is, hey, this hydrogen here has two places to go. There's one oxygen here, there is another oxygen here. But why is this hydrogen showing interest, particularly on this oxygen? This is my question. Patty, you're on the right track, but I want you to examine the scenario closely. Forming a bond right here is yeah, I would say it's a consequence of this electron pair coming over. Okay, now Nathan, did you say the lone pair? Yes. But Nathan says, does the double bond add another electron pair? Yes. Nathan, you got it right. Nathan gets 1 point. I want all of you, woohoo, it's not easy, okay? Look at hydrogen plus. It's very, very naked, am I right? This is a positive charge, naked by itself, am I right? Proton by itself, very naked. And so it doesn't have any electron at all, so it's actually very hungry for an electron. All right. But Nathan says there's a double bond. Yeah, in addition to the lone pair, it has a double bond. So the electron density in this area is high. Am I right? Do you agree? Yes. Nice job, Nathan. You got it. Because the electron density here is high with the double bond. Yeah, this oxygen here also have dot, 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 lone pair. But so what? You and I are equal. But this electron pair extra will attract the hydrogen to come near this area. Boy, it's hard to get that answer. Okay, Nathan, you did a very good job. Okay, so look at this. Look at this process. Once you form a bond in between plus charge right here, and definitely will pull. Okay, and that's why I said to Pity, you are actually talking about the consequence. Okay, you're not looking at the root cause. The root cause is that, okay, electron rich attract proton. And so once you have a good electron pulling force, the driving force, alcohol will come over. Definitely, definitely attract that alcohol naturally. Okay, nice job, nice job. Okay, attract, and then what's going to happen to the central carbon right here? The central carbon will say, wow, look at my neighborhood. Oh, oxygen, oxygen, oxygen. Oh my goodness, I'm surrounded by 3 oxygen. Am I going to be comfortable? Let me tell you, this carbon says, yeah, you're pulling, you're pulling, you're pulling. I will experience a lot of pulling. Okay, someone help me, okay? I'm not comfortable. All right, then let me tell you. Let me tell you what happened. You see OH and OH right here. And guess what? The hydrogen from the environment, either from the acid, extra acid you provide, or either from alcohol also, with this lone pair also can be a parking lot of that extra hydrogen nearby. And so, yeah, additional hydrogen can be provided here in order to create water as a leaving group. Understand? If you ask me, is water as a leaving group being a good driving force of a chemical reaction? The answer is yes. If you have a good leaving group, such as water leaving group, or CO2 as a leaving group, okay, or precipitation reaction as a leaving group. These are all good driving force of a chemical reaction. You see that? Okay, so such a thing can happen, okay? The hydrogen plus, okay, either internally transfer, oh, that can happen too, okay? Or it can hop between alcohol and then go back to the hydroxy group somewhere in the molecule and create that water leaving group. So the ester will be created after the water is generated, okay? And to remember, you have the plus charge still, okay? Coming from all these, okay? And now you have the oxygen here with plus charge not comfortable. It needs to, okay, give away this proton back to the solution. That's why hydrogen plus is a catalyst. It gets regenerated, okay? And this lone pair gives back and making this oxygen plus satisfied and happy. And with this hydrogen generated back, you can produce the ester at the same time. Okay, so who is receiving that hydrogen plus? It's either the alcohol or the surrounding water molecule. Okay, remember you create water as the A side product, so the water is there. Okay, it's there. If it is not pumped out, it's there. Okay, I can tell you, it doesn't matter how good you are. It's really hard to get rid of all the water. created from this esterification reaction. It's so hard, okay? At BP, oh my goodness, it is always the moisture level we always have to report at the end, okay? It can be as high as 0.1% a lot of times, okay? We start out with, anhydrous glacial acetic acid or something like that, moisture-free. But the water created from this reaction, it cannot be pumped out 100%. No, it doesn't, okay? And we have to live with it, okay? And so, are you able to understand the mechanism? Go ahead. I think this is all in the lecture of your, your lecture professor. They will give you the slides along this area, along this line, okay? And this is also available on the Google, okay? Ester is a very common experiment, so you find this information readily, okay? I just don't like this part, okay? All right, so far so good. I hope you learned that reaction, okay, with this mechanism writing, with these photos, I think it serves the purpose already, okay? You're not able to collect the product, but so be it, okay? We're not living in a perfect world, and we're tough, so we can deal with it, okay? Yes. Let's go, team. Dr. Jane, can you move the product to non-polar solvent to remove the water? Oh, then you're dealing with another set of cost. Understand? No, you're dealing with the solvent you cannot get rid of 100%. Understand? Too expensive, yeah. Can you imagine if your banana oil is contaminated with solvent? You think your customer will buy it? No, they don't want it. Okay? Money rules the world. You're right. You're so right. And the thing is, water is harmless to the product, but we know the solvent may be harmless to the product. You know that? Because people then worry about, hey, what is the consequence of drinking this banana oil with some solvent in there? And then you're dealing with another set of problem. We hate it, okay? But this is I can tell you, a lot of people just make money out of running the esterification reaction, okay? All you have to do is find the reactant pair together, and you may be able to produce some smell that, it's not coming from natural resource. You may be able to create some flower smell, but that's not coming from the plant, okay? It's a lot of money, okay? It's a lot of money associated with ester in industry. I mean, the money means business, okay? It's a lot of business associated with this, okay? And I really enjoy it, okay? And so let's go back. Is there anything else I should talk about? Let me see. Oh. I want to talk about the worksheet. Okay, the worksheet. All you have to do for indifference compared to the regular semester format, we do everything the same. Okay, you calculate the yield the same way. Please do not skip theoretical prediction. If I ask you to do theoretical yield, I just want you to do the calculation based on the amount suggested in the lab manual, okay? You just don't need to provide the grams at the end, the actual yield. That is 0, we don't do anything, okay? That is 0, but you have no penalty. You receive no penalty reporting 0. but everything else should be the same. You report the boiling point based on the number you looked up, okay? And you write the mechanism according to what you learned, okay? Do everything the same, okay? Is that good? Okay. Okay, no problem. Okay. And next lab, no, sorry, not the lab. Let's plan to do this. When we do our class meet next time, that's after the spring break, I will take questions from the floor, okay, from the chat room, and I will answer a question. At the same time, I want to go over some of the common mistakes from the NMR. I want to show you, yeah, some of the answers I saw. I already finished grading your first visit. Some of the questions were not answered perfectly, especially the symmetry part, the molecular symmetry. That is question number 1. I asked you how many different kinds of carbon, how many different kinds of hydrogen, etc. Oh, some people didn't do well, okay? So I want to touch up your understanding, NMR, next time, okay, on the discussion part. And at the same time, I want you to do the worksheet. And so you can prepare to ask questions when we do day 2. Do you hear me? There will be spectrum NMR question, peak assignment, the same thing, okay, the same. It's the same as usual, okay? Just do questions and then prepare to ask questions. And day 2, I will talk about NMR, mistakes from what I, you know, when I collect your reports. I feel sorry for those who didn't really have a good chance to work on the questions, okay? And I want you to catch up. The reason is in the final exam, there will be 6 or 7 questions out of 30 multiple choices. They're from NMR chapter. That's why I want to touch it up, okay? Because if you fail, that means if you don't learn well, that means you lose 12 to 14 points out of 60 points. That's bad news, am I right? When is the worksheet due? It's written exactly on the revised schedule. It will be a day after day 2. Is that good? That's enough time, okay? That's enough time. And I want to make this discussion session on day 2 as fun as possible, okay? As much fun as possible. I think, yeah, on day 2, we don't really have much to talk about from this experiment per se. But the NMR, okay, the NMR will be a problem, yeah. Before we go, can we see your puppy again? Oh, yeah. You like my puppy, huh? By the way, I want to know, because I've received this warning that the internet connection was not perfect. Are you able to see my puppy now? Hello. She's an angel, okay? She's an angel. And I think I told, what is his name? This is a girl, okay? Her name is Ribby. It means rib eye. Do you know what rib eye is? The steak, okay? This is actually the favorite part of my son. I mean, my son loves no, he enjoys steak. Okay, the rib eye is okay, or filet mignon, and so this is rib eye, bulgogi, my baby. And tell you what, I think I shared with Amanda once. Or Faro, you remember? We were talking about my puppy, because I brought my puppy to school 2 times, and she refused to enter the building, the HSCI building, because she didn't like this. She didn't like the building. She hates the smell. So you and I don't smell it, but the dog can. The smell of the toxic substance. She refused to go in the building, enter the building. So I always have to hold her in my arm entering the stupid building. I'm not joking, okay? They know, their nose can tell, okay? And so I was amazed. Not only that, when she joined my family, you know, my son bought this dog. And when you know, this is, you know, in my whole life, this is my first dog. Okay, it's not my dog, it's my son's dog. He bought it in order to entertain the whole family. Okay, and guess what, it was the first time experience I realized, hey, they smell what we cannot smell, they hear what we cannot hear. So if the neighbors walk their dog and cross my house at front yard or on the street, even from long distance, she can hear it. And she will start barking or make a lot of noise, running around. And you know, in other words, remember the visible light. When you learn this, the visible light between 400 to 700 nanometer visible light to us, they can see what we cannot see. They can hear what we cannot hear, etc. Okay, so amazing. Okay, and so they're smart in a way. That's why they have this service dog at the airport. They're able to spot the drug smuggling. Yeah, yes, they are different. Okay, they're built differently. And so for today, well, 1, 2, 3, 4, 5, 6, 7 students got bonus point, okay? And did I tell you, I really want to see students' potential right here, okay? Last semester, the bonus point maximum, I mean, students were able to, one student were able to pick up 11 points during the semester. That was amazing, okay? And I want to encourage you to interact and ask a question, okay? Before we say goodbye to each other, do you have any question? Hello? None? Only if dog could be chemist. All right, do you like this chapter so far? Not bad, right? It's wonderful, right? Best Zoom ever. You know, I want to tell you, the best way to handle crisis in your life is to look at this opportunity as a training experience. Okay? We know it's tough, okay? But only when you go through this limit, you realize you are far more capable than you think. Do you agree? Perfume. Love it. Yes. Okay. So we will be tough after this process. Okay. And someone, okay, just in case I forget, I promised you a party that we should get together. Can someone write to me? And I don't know how to keep everybody in the same room anymore. After the semester, I don't know, okay? So how do we interact, contact each other? Zoom party? No, we're talking about real party. It's just what, we have to find out whether it's illegal to drink in public or something like that, okay? Yeah, okay. Anything else before we say goodbye? Farrell is very organized. I can tell you, a lot of you are very, very organized. Yes, real party. Yeah, we find it. Okay, once you have the vaccine, we never know. Yeah, I can tell you. Yeah, something is cooking up to cure the disease. All right. Oh my God. All right. Anything else before we say goodbye? I will see you after the spring break then. All right, now tell me, do you think it's absolutely necessary to upload the video? I try. But the thing is, I keep getting this note saying this internet or the uploading is causing a problem. Okay, I can show you what I read today from the screen when I try to upload the video. The Zoom recording is what I mean. Are you able to see this part? It says, oops, we're having trouble connecting you. You might want to refresh the page or try again later. I can tell you for 4 days I tried this. It didn't help. I don't know what happened, okay? It will be helpful, I know. We would like to have it up so we can, re-listen. I will try, okay? Try to understand. I have the recording on my laptop and I have problem uploading it. This is I have no idea what happened, okay? So if you have any clue how to fix it, can you write email to me? All right? Is that okay? You could put it on a Google Drive link. Megan, I wish I have that capability, okay? The thing is, Miss Jean is in the middle of so many crises. Tell your neighbor to turn off her Wi-Fi. Oh, they probably asked me to turn off my Wi-Fi too, okay? Okay, in the name of science. Yeah, guess what? A lot of people work from home nowadays. There's a problem. I even need to schedule with my family members. Hey, because I have an important lecture. So anything else you want to do, please. Okay, try to give some consideration to my students. Okay, I did request that. That's why my husband, my son, they're all gone. They don't want to be in this house. Okay, they probably went to Starbucks. All right, and anything else? So Megan, if I set up this Google Drive link for everybody to view it, not through the Zoom, I have to figure out how to do that. I'll ask my son. He's quite digitally savvy. Tell your neighbors. No, I can't. I can tell them to turn it off, okay? Or YouTube account. We'll see. Okay? Oh, that will work too. Yes, true. All right. May I say goodbye to you now? Any other question? Any other question? Okay. Not really. All right. Thank you. Bye, Professor. I'll see you next time. Okay? And have a good spring break. All right? Bye-bye.